Hello, my name is Selena Wu, and this is my presentation for the Lines of Charge Lab. Experiment Introduction. The purpose for this experiment is to determine how much excess charge is on a piece of tape. To find this, I charged one piece of U-shaped tape by removing it from a U-shaped base tape on the table. When I put my hand up to the tape floated closer toward my hand. However, when I placed two U-tapes side by side, they repelled each other. And when I placed a pen rubbed on cloth next to the U-tape, they were attracted. Therefore, we can conclude that the U-tape is positively charged and it must have a deficiency of electrons. In this experiment, we suspend one tape in the air by its ends and another piece of tape is brought under it, pushing it upwards. At the instance when the top tape appears to float upwards, it is repelled by the electric field of the bottom tape, and the distance between the two tapes determined that the charge of each piece of tape was 0.2268 nanocoulombs. Experimental values. We find that the length of the tape was 0.2 meters, that it had a mass of 0.0002 kilograms, and that the distance between the two tapes when the top tape began to float was 0.0204 meters. Additionally, the magnitude of the gravitational force on the floating tape and the magnitude of the electric force on the floating tape are both 1.96 times 10 to the negative 3 newtons. Assumptions and physical principles used. Firstly, we assume that the U-tapes act as line charges. In reality, there are many places on each piece of U-tape that have an electric field and that apply the force of that electric field to the other U-tape. We represent the U-tape as a line charge consisting of 20 point charges spread out an equal distance from each other along a 0.2 meter piece of tape. We assume that the top U-tape and bottom U-tape have the same charge, and it is reasonable to make this assumption since both pieces of tape are of equal lengths and charged in the same manner. Both are pulled off the same base tape. Additionally, we assume that the U-tapes are subjected to only the force of the electric field of the other U-tape and to the force of gravity. We ignore the presence of other electric fields due to the tape's surroundings. To solve for the charge of the U-tape, we apply Coulomb's law and Newton's second law. Coulomb's law provides the equation for calculating the force of an electric field, and Newton's second law explains why the forces should be balanced. The momentum of the top tape is not changing and the tape is not accelerating. Therefore, as stated by Newton's second law, the momentum principle applies, and we know that the net force acting on the tape is zero. Thus, we find that the force of the electric field and the force of the gravity on tape B balance out, making the net force equal to zero. Finding U-tape charge. From there, we find the force of the electric field of each of the 20 individual point charges acting upon the top U-tape and apply superposition to find the net force of the electric field acting on the top U-tape. Additionally, we may use the formula for the magnitude of gravitational force on the top tape and set this equal to the magnitude of the net electric field force on the top tape, as found by superposition. Finally, we can plug in values for the charge of the U-tape into our computational model, and we find that the charge of each U-tape is 0.2268 nanocoulombs. GlowScript code demonstrates how we reached our result, firstly by listing physical constants and the measured values for our experiment. Additionally, this is where we can plug in charge values for our U-tape to make the net electric field force and gravitational force balance out. Here is my code that I used to find the electric field of one single point charge on the U-tape. Next, we have a function that creates the uniform sphere spread out over an equal distances along the length of the U-tape. This function is called by two variables, top tape and bottom tape, that display 20 red point charges and 20 blue point charges, each representing two tapes, a distance d from each other. The for loop shown in this code iterates through the 20 point charges in the top tape and calls the e-field function to find the electric field of each point charge and then sum them together. This code is applying superposition to find the net electric force of the line charge of each tape, and then creates a cyan arrow in this line to represent the electric force vector at each point charge. Lastly, we display the net electric force vector of the top tape as found through superposition of the point charges, and the gravitational force vectors as white and yellow arrows respectively. The charge of each U-tape as calculated by the computational model is 2.268 times 10 to the negative 8 coulombs. This is true since when the U-tape has this charge, the magnitude of the electric force and of the gravitational force are roughly the same. Both vectors representing these magnitudes appear as equal and opposite, and the cyan electric force vectors of each point charge appear to add up to the white net electric force vector. Reflection. If the tapes were modeled as a single point charge like in experiment 1, the calculated charge of the U-tape would be much smaller, at 9.52 times 10 to the negative 9 coulombs, than the charge of 2.268 times 10 to the negative 8 coulombs found in this experiment, where the tape was represented as a line charge. These estimates differ since they are based off of different assumptions and require different calculations. Point charges utilize a simplifying assumption that places all the charge at the center of the tape, while the more accurate representation of the tape as many charges spread out along the tape accounts for the fact that many charges from the bottom tape are acting on the top tape at the same time from different positions. Therefore, the line charge estimate is considered closer to the real value. Finally, we reached the result of this lab to be that the charge of each tape is 0.2268 nanocoulombs.